Datum Located Features. Feature templates are where the software thinks the feature should be. As standard, this is based from the program reference system. However, we can change this to use a datum or datum frame instead, just like a variable. In this first example, we're going to be measuring the highlighted bore as a circle. We will fix the height of the measurement to a specific offset from the bottom face of the bore. We'll set our reference system as so: a plane on the top face as datum A, a circle on the large bore as datum B, and a line on the front face as C. The goal of this example is to fix the height of the measurement to always be 5 mm from the bottom face. As standard, this would create the programming code to measure the circle at Z minus 15 mm from the top reference plane. However, if the depth of the bore changes, in this example to 21 mm instead of the nominal 20 mm, then the 5 mm offset is no longer correct. This is due to the feature template still being set to 15 mm from the reference system. This can easily be resolved by measuring the plane at the base of the bore and defining it as a datum. We can then apply this datum to the feature template, so the 5 mm height is always maintained. So let's see this in action at the CMM.
So this is the real world example on the CMM. So you can see I've already measured the reference system, which is the datum A plane, the datum B circle, and the datum C line. What we're going to do now is just go in and measure the plane at the base of the bore. So for this I'm just going to take 4 points, and then we're going to measure 2 circles. So that's the plane, hit the green tick, circle, we can use the auto measure here. So the goal is we have 2 circle measurements. One will be a standard measurement, which is only linked to the reference system, and then one will be a datum located feature using the Z plane for its height. So that's the first circle. We then just repeat this measurement again. There we go. So what we'll do, we'll go over to the software now. So there we go, so we've got the plane, 2 circles. So what I want to do first is I want to define this plane as a datum. That will allow me to reference it later in the second circle measurement, so I can link the penetration to the actual plane, and the only way we can do that is by defining it as a datum. So we just double click that plane, define it as a datum, and just to save any datum letters that might be in the application, I'll go right down to Z or Z and define that as Z. So there we go. Let's prioritize the XZ view here. So if we right click on the first circle, just to show you how this functionally works, the software has projected it into feature number 4, that's the base plane. So that's why you're actually seeing it projected down into that bottom plane and not the top plane. So what that does is it gives it a rough idea of the template of where the circle should be, and then the penetration is the kind of offset from that at where it's going to actually measure it. Now the confusing thing here is this code that it runs, i.e. these coordinates, are all based off the reference system of the component. So it's not actually linked to feature number 4, it's just that it's being projected into it. So what I mean by that is if I put -5 in here, the theory is that it should give us a -5 offset from that face, and the way we can check this is if we create a surface from that circle. So this was circle number 5. That will actually pull the data points from that, and if we dimension from the plane to the point, that gives us a height. So if we change this and call this standard feature, helps if you can spell. Standard feature, let's say it's supposed to be 5 plus or minus 0.1, and if I right click on that circle, we've set it to 5. If I run that back, in theory it should be 5, and it is. and that's because that plane is as it's measured. Now if we were to change this now, this would not stay as 5, i.e. if Z moves up or down, it doesn't actually change this. This is staying fixed to the coordinate system of the part. So what we want to do is we want to actually measure the circle and link it to Z. That's what we're going to do with the second circle. So if we right click, choose unit 6, go into CNC. So we're going to use very similar parameters, only we're going to utilize this datums box. So you see datums, and in theory we need to define all 6 degrees of freedom, but if we do just change to Z, all it's going to change is the Z value. The X and Y and rotation are still taken care of by the reference system, so in this example we can get away with just setting Z, and you'll see there the template now changes. So instead of being -20 as it was supposed to, it's gone to 0, and when we put in -5 and hit make, you'll see the code here doesn't read as -15 anymore like it did on the previous circle. It means it's reading the position of the coordinate system but shifting the plane to now align with Z. So that's the datum Z. And then it's going to go -5 up, which gives us a +5 value in the coordinate system. And it's always going to fix the 5 in relation to Z. That's the really critical thing. So now that that's done, we can rerun that. And there we go. If we do the same thing now, so surface, construct, from the unit 6 circle, hit the green tick, and if we dimension from here to the most recent surface, you'll see we have the datum located feature. So because this is the very first time we've run this, you'll notice these two are very similar, and that's kind of what you would expect. But what I'm going to do now is I'm going to switch the camera back on, and you'll see this now. I have some packing pieces. So I've got 2 of these small little discs, about 250 microns thick. They're just some laminated paper, but it's to kind of prove out the theory. So if I drop one in here now, and then we press play, and then view the sizes. There we go. So what you'll notice is the offset from that difference in the measurement of the plane has not affected the datum located feature. That depth has always stayed the same, but the standard feature has changed, and that's because when we run the dimension to the planes, it's no longer 20 anymore. It's been bumped up slightly. So just to go through it one more time, so if you note these values, this is still 5, but this is 4.8. If I now pack up another disc, so again just another packing disc, I'll insert this in just to verify or replicate a change in where the Z plane is or has been machined or manufactured. So if I run this now, and there we go. So you'll see again that height has changed, so where Z is in relation to the reference system, which has caused the height of the standard feature to change once more, because again this is going from the reference system, not offset from Z, but the datum located feature has maintained that 5mm offset. So hopefully that clarifies how to control depths or Z heights for circles and other features. And now we can look at the second example, which covers XY position.
In this next example, we're going to be measuring the depth of the internal pocket. This will be done via 2 circular planes. The reference system for this component is as so. A plane on the top face as datum A, a line on the left hand face as datum B, a line on the back face to allow the datum C construction, and a constructed point where both lines meet to give us datum C. The template for both circular planes will initially be fixed to the reference system. This would be 90mm in X and 40mm in Y. Whilst this should work okay, it is prone to crashes. If the entire pocket shifts, the circular plane templates will stay as they are. This can easily be resolved by measuring the first bore of the pocket and applying it as a datum. We can then use this to fix the template of the circular planes. This means the circular planes will always be linked to the datum bore. So if the datum bore moves, then the circular planes will always move with it. So let's see this in action at the CMM.
So in this second example, we are going to link the position of some circular planes to a datum frame rather than the reference system. So in this example, the reference system is the plane on the top, that's datum A, a line along the left hand side, which is datum B, and an intersection point at the corner, which is datum C. So anything we measure as standard now, the template of where to go and measure the feature will be linked to that coordinate system. So that will be our XYZ 0, and that makes a huge difference on things like this pocket. So imagine this is like a face groove and I want to measure this plane. I'm going to be going very close to the edge of this circle and the sphere when I take the two circular planes, and if that was to drift at all, say it's been done in a different operation, etc., the likelihood is it will crash. So I want a way to be able to zero out so that the position always stays true to itself. So say this pocket with all the PCD holes and this groove are all done in the same operation. I want to link the measurement path and the template of these circular planes, so an inner and outer, to be linked to this bore. So the position is no longer linked to the datum or the reference in the corner. It's going to be linked to this larger circle. So let's dive in and have a look at that. So we've measured the reference system. So again, to follow the example, it's the datum A plane on the top, the datum B line, so that's side left hand face. We've then measured the back face as a line and constructed a point where the corner meets, and that corner is the datum C reference origin. So what we need to do now is firstly measure the larger bore that we want to zero out the positions for. We can then apply this as a datum and then apply that datum to the features so that the features are located via the datum frame versus the reference system as they would as standard. So let's just switch the camera on. You should be able to also see the feature. There we go. And all I'm going to do is just drive over, and again, just for this exercise, I'll just take 4 points. So there we go, we hit the green tick. I'm then going to measure 2 planes, and to do this I'm just going to define 3 points, one on the sort of outer edge. Imagine these like a triangle. There we go, hit the green tick. Another plane slightly closer in. Again, like a triangle, as that will define the 3 points required for the circular path that I will modify. So there we go, we have everything we need measured. So let's come out of the camera and look into the software now. So again, just to show you what would happen without using datum located features, if I right click on both of these planes, so let's start with the outer one, and I go to CNC and change it to circular, you'll see this position of where the circular center is and the diameter are all linked to the reference system. So the points and the template are all linked to this origin, this datum C, via the alignment of B and obviously the primary alignment of A. So if we leave that as it is now, we've got no way to zero it out on this central bore. So if this bore and on all the features with it are done in a different operation and it moves, 1 millimeter to the left, when we run it, this plane will crash. So we want it to be able to zero itself out every time it measures this circle. It then knows exactly how to center these two circles. So the only way we can do that is via the datums box, so that we can locate the template of these features to the datum frame. So firstly, we'll change these both to circular. So you can see the pictures there, or the graphics. And then we need to define this as a datum before we go back in and modify these. So if I define this as a datum, and again, to save datum letters, I can go straight down to Z. It obviously depends on your application, but in this case, I'll just use Z. And all I really want to do in this is use the A, Z, and B datum frame, because the Z is going to overwrite the C origin, and then it allows us to have a X and Y 0 for these two, so that they're always centered on Z. So let's see this in action now. So right click here, we'll go to datums. Now again, make a look or make a note and view this. So this position currently is from the reference system, but if I apply A, Z, and B, the template now changes. So if I say 0 and 0, that means the central position of this circular plane is always going to be zeroed on wherever Z is measured. So once it measures Z, it can then zero out this plane. So template positions, hit make. That's that one done. And then right click here and we're going to apply the same thing. Now what's useful is the software actually remembers those datum frames. So rather than selecting all three letters again, we can just add AZB. You see that updates there, and we can zero these out. And now we know every time we run this program, these planes are always going to be centered on wherever Z is. So just to see that in action, so if we just hit the green tick now on this, and I'll switch the camera on. See the features here as well. Let's run this program. And there we go. So if I just switch that off now, there we go. So again, you'll see these now are centered on this datum Z. And if, say, we wanted to measure this as a plane, just in the previous exercise, we can either construct as a surface, or we can construct the plane using from feature points to do a combined plane and get the correct height. There we go. But that is always now going to be fixed. So just to showcase this again as a sort of real world example, what I'm going to do is just slightly move the job. Can't move it too much, otherwise I need to mess around with the pre-travel, but this is well within the sort of manufacturing variance you can see. And if I just run this back now from the Z circle, so play from here now. Okay. So this now measures Z in a completely different place. But you'll notice here the plane's on catching the edge of the inner circle, or here on the sphere, because they're able to re-zero themselves on wherever Z was measured. So there we go, nicely done. And that again updates, and the position is ideal. It's perfectly centered. These paths are perfectly centered around Z. So that is datum located features for a positional fix.